Hello, my name is Ximena Gutierrez, and I'm going to talk about languages through the looking glass of BPE compression. Our work starts with subword tokenization, a standard preprocessing step in NLP. We know that splitting orthographic words into smaller units is a way to improve the input for NLP systems. Some unsupervised methods have approached this as a data compression task. Compression algorithms exploit redundant patterns, and while doing this, they uncover regularities in the data. A popular method for uncovering subword units is BPE, which merges sequences of co-occurring characters through incremental operations. In this work, we inspected more closely what kinds of structural elements are exploited by BPE across many different languages. Our hypothesis is that the properties of the subwords found by BPE are not the same across languages. In fact, they depend on the morphological type of the language in question. This is important since if these patterns turn out to be indicative of the morphological typology of languages, then we can do data-driven induction of typological knowledge in a resource-cheap way. Counter to the intuition that BPE subwords are not linguistically relevant. To test this hypothesis, we first need to quantify the subword properties. We achieve this with a novel method inspired by the notion of morphological productivity in linguistics. After this, we vector characterize languages based on the properties of their BPE subwords. And finally, we assess to what degree these language vectors encode the known morphological types of languages. So let's go quickly through these steps. First, for each subword found by BPE, we calculate productivity as the number of orthographic words that contain the subword that is being merged in the current operation. This second measure is a cumulative frequency over all the word types that contain the current subword. Idiosyncrasy is simply the division between them. So, for example, this subword ED at the end of the word is highly productive because it is contained in many words. This is similar to a morpheme that can be applied to many different lexemes. ED also has low idiosyncrasy. In a three-dimensional space, we will find this type of subwords in the circle area. In contrast, these other type of subwords are contained in few word types, but those types are super frequent. That's why they have high idiosyncrasy, and we will find them in this region of the space. So using this operationalization, we can plot all the subwords for each language. In this example, we are showing the subwords created during the first 200 merge operations for 4 languages. We focus on the first operations because they are the ones that achieve the most significant compression of the text. What we notice is that for some type of languages, the compression can be achieved via productive subwords, those patterns that resemble inflectional markers, affixes, and regular morphological phenomena. For other languages, the compression is achieved by harnessing idiosyncratic subwords, those that correspond to frequent irregular patterns or whole orthographic words, which are highly redundant due to their high frequency in the corpus. If we average these values per each language, we obtain a single language vector representation. In this BPE space, we can see that languages like Halali Sud or Quechua are in the region of high productivity. Languages like Vietnamese or Thai are in the regions of low productivity and high idiosyncrasy. Most Indo-European languages tend to cluster in the middle, just to mention a few. So if there is a connection between VPE and the structure of language, there should be a good agreement between the language vectors that we created and independent language vectors derived from external linguistic knowledge. So in quantitative terms, we evaluate this agreement by creating language vectors using features extracted from a typological database, WOLS. So we cluster the language vectors in the BPE space and in the wall space, and we use the mean silhouette coefficient to check whether languages clustering together in the wall space are also neighbors in our BPE space. According to our results, language vectors created with as few as 200 BPE merge operations show already good agreement with the wall space. This suggests that we can have language vectors that encode typological knowledge induced from simply raw text. Interestingly, the same amount of incremental patterns obtained from the workpiece merging criteria are less indicative of the morphological structure. In a more qualitative fashion, we conduct exhaustive analysis of how our observations relate to the morphology of languages. For example, we interpret our productivity measures in terms of categories established in the typological literature, like the notions of synthesis and fusion. Our work offers a quantitative yardstick for the categorical features of traditional typology, showing that it is possible to induce typological knowledge from raw data and a compression algorithm. Thank you.